Hello class, welcome to today's lesson. Today we're going to finish with the topic 2.11, which is transformations of graphs. And today we're going to look at the stretch, also known as expansion or dilation. Okay, so you have to get used, I think I have already told you this, in mathematics also as in normal language. Unfortunately, sometimes there are many words for the same concept. And so if you think you don't know a particular word, you have to look it up and see whether they are telling you the same thing that you know already. Okay, so stretches, expansions, dilations, they all mean the same thing. Okay, so far what have we seen? Let's consider this blue graph, which represents the graph of a function. And so far, the only transformations that we have seen are translations. For example, the vertical one, if we have this function, this parent function, I can translate it upwards, translate it downwards by whatever amount of units I desire. I can translate it horizontally to the right, horizontally to the left. Okay, and those were translations. Also, we have seen reflections. If we reflect this function over about the x-axis, it should look like this, right? More or less, you get the idea. So let's go back. And if we reflect it about the y-axis, we should get this. And that's what we have seen so far. So translations and reflections. Now let's go to stretches. Okay, let's go to my graphing calculator, and let's consider the function f of x equals the square root of x. And remember, when we consider this particular function, we only mean the positive root of x, because remember that the square root of x, when the index is even, for example, the square root of x, or the fourth root of x, or the sixth root of x, and so on, you always get two solutions, okay? And in order for this to be a proper function, we should only consider one of them. And in this case, I'm going to go for positive. So the graph of this function looks like this. And if you remember, we had a way, like I said a moment ago, we had a way to translate this function, or the graph of this function, upwards by whatever amount of units I want. So let's suppose I want to translate it 2 units upwards. What I should do is write the same as f, and then I'm going to add plus 2. You see? And you get the new transformation by adding 2 to the function that represents this graph. Okay, that was easy. Now, if you notice, guys, I'm going to go with my tool. If you notice, if you pay attention, what this transformation is doing, this is your parent function, okay? This is my original primitive or parent function, and this is the transformed function. By adding 2 to my original function, what is happening? Basically, what is happening is that each of these points that comprise or that make up my function, each of these points, I'm just locating some of them. Each of these points are being translated to units upwards. You see, this one goes here, this one goes here, this one here, and so on. And if you notice, basically, all that we are changing about these 4 points, are the y coordinates. You see, because the only difference between this point and this point is only the y coordinate. The x coordinate of this point is 1, and the x coordinate is 1. The only thing that is changing is the y coordinate, and the same for the rest of them, okay? All of these points in here, that's what's happening. They are being moved to units above or upwards. Okay. Now, what if you say, okay, I do not want to move these points to units upwards, all of them. Okay, I don't want to add 2. to the y coordinates of all of these points. What I want to do is multiply by 2 each of the y coordinates of all of these points of my parent function. Let me get rid of this transform function for the moment. Okay, so I go back. What I want to do is take these points that make up my function, all of them. I'm just signaling some of them. And now what I want to do is the y coordinates, I want to multiply them by 2. So for example, what is the y coordinate of this one? Is 1. And if I multiply by 2, then that transformation should put it right here. Okay, that transformation will move this point towards this place. Now this point in particular, what is the y coordinate? Is 2. And if I multiply by 2, such coordinate and only that coordinate, this point should be moved over here. What about this one? What is its y coordinate? It's 3. Let's multiply by 2, we should get 6. So this point will be displaced towards here. And the same for the rest of them. Now, if I traced that resulting function by doing such transformation, multiplying the y coordinates of all of these points by 2, what I'm going to get is more or less something like this. You see? Which is not the same as translating each of these points to units above. Can you see? So how can we achieve this behavior, this new transformation? Well, I can go over here, and I will no longer, again, this is a translation, okay guys? This is a translation of this function, but I don't want that anymore. What I want to do is an stretch, a vertical stretch, which is what I did in here. What I did in here by creating this yellow function, or this yellow graph of some function, is basically stretching my original function, which is this, along the y-axis. You see, I'm stretching only the y-axis, and in order to do that, what I need is to multiply. In this case, multiply my original function, which is the square root of x, by the scale that I want to stretch my function, which in this case is 2. So let's see. You see? And what is being created is exactly what I said before, more or less, right? You see? I'm going to get rid of my drawing. There it is. So this is my parent function. This is my transform function. And what is the relationship now? That this transform function is an expansion or a stretch, a vertical one, with respect to this one. Okay? Each of these points in this function, in my original function, are being stretched only vertically. In other words, only the y coordinates of all of these points, only the y coordinates are being multiplied, in this case, by 2. You see? So this y coordinate times 2 gives me this. This y coordinate times 2 gives me this, etc. And that's why the 0 remains as the only coincidence, right? Because this point being 0, its y coordinate is 0, and 0 times 2 will be 0, right? So it's going to be the same, you see? Okay, so that is what we know as a vertical stretch, in this case of a scale or a factor of scale equal to 2. That's what it looks like. Now we can also do the opposite thing. I can actually make a stretch or a compression, in this case more or less, by a factor of 2. And what that would mean is, in this case, like instead of multiplying the y coordinates of all of these points, what about dividing over 2? For example, we have this, the y coordinate is 1. If we divide over 2, we're going to get this point, this new point. Look at this point, its y coordinate is 2. If we divide over 2, we're going to get 1, which is this point. What about this one? Its y coordinate is 3. If we divide over 2, we get 1.5. And so the new transformation will look more or less like this, which could be said to be kind of like a compression, you see? a compression of my original function. I want to flatten it out, so to speak, by a factor of 2. And in order to achieve that, what I need to do now is create function h of x. And instead of multiplying by 2, like in here, I'm going to multiply by 1/2. 1/2 times the square root of x. And you see, we get that such thing, in fact. Okay, so now this is also a vertical stretch. Okay, but now the factor is 1/2. And you could, when you have a factor, a fractional factor like this, like 1/2 or 1/3, etc., or anything below 1, between 1 and 0, you could call it a compression. Okay, you can call it a compression of my original function, which is this, a compression of factor 2. Or you can call it a stretch of factor 1/2. You see what I'm saying? Don't get confused. I'm going to repeat. This is my original function, and this could be called to be a stretch with factor of scale 1/2 or a compression of factor 2. The most usual one, though, is a stretch of factor of scale 1/2. Okay, guys, so that's what we know as vertical stretch. And let me give you quickly another example. We have this function that represents half a circle. Okay, we haven't seen this one. It's pretty cool. And I'm gonna do the same. I'm gonna create two functions that are gonna vertically stretch this circle. So first, I'm gonna stretch by a factor of 2. So this thing, which originally looks like this, will now have to look more or less like this. You see? This point, let's look at some points. For example, this point 4, if I stretch by a factor of 2, we'll go over here. What about, I don't see any other. Well, this one, its y coordinate is 3, you see? And if I multiply by 2, it will go to 6, more or less here. The same for this one. This one right here will go over here, kind of. So it's gonna look something like this. An expansion of factor 2, or a stretch with factor of scale 2, should look more or less like that. So let's see if it works. Let's multiply 2 times f of x, because I don't want to write the whole thing. There it is. You see? This is my parent function, this thing, and this is my transform function, and this represents a stretch, a vertical stretch with factor 2 of my original, with respect to my original function. Now let's do the opposite. Let's create a function which is going to be the same as f, but with a factor of scale, a vertical stretch with a factor of scale of 1/2. There it is. You see, we are compressing our original circle. You can call it that way, compressing it, or a stretch with factor 1/2. So that's how it looks. So this is what we know as a vertical stretch, guys. Now let's go back, and now let's talk about horizontal stretches, because if we did that by taking into consideration only the y coordinates of these points and multiplying them by some constant, I can do the same but with the x coordinates. Okay, if I want to multiply, let's look at this point. If I have this point and I only want to multiply the x coordinate by 2, then this point will be transformed into this one, right? What about this? You have this point. What is the x coordinate? Is 4. And if I multiply by 2, only the x coordinate, I'm gonna be having this point. So this point goes here, this point goes to here, and so on. So on for the rest of the points. So my transformation should look like this, more or less. And this is what is known as a horizontal stretch. Now this is a horizontal stretch. And how does that work? Analytically, what we have to do now is do the change, but on the variable, inside the variable, okay? And in this case, it's gonna work in the opposite sense. If we want to make a stretch of factor 2, we have to divide the x over 2, like so. You see? You see how they coincide? Okay? So if you want to stretch a function by a factor of 2 in the horizontal direction, what you have to do is divide your variable x over 2. All right? And if you want to do the opposite, if you want instead to compress your function in this way, for example, if you have this point, and if you want to apply a transformation to the x coordinates by dividing each of the x coordinates by 2, then this point will go here, right? This point, having x coordinate equals 4, will go to 2, and the rest of them, you see, this point has x coordinate 9, and if I divide over 2, I get 4.5, which is here, and so on. So now that the horizontal stretch will look like this, more or less. And in order to perform this analytically or in the function, what we have to do now is multiply by 2 the variable, only the variable, like so. You see? You see how they coincide? So that's how horizontal stretches work. Please be, I mean, you have to pay attention, a lot of attention in here. If you want to, talking about horizontal stretches, if you want to stretch your, let me get rid of this. If you want to stretch your original function by a factor of 2 in the horizontal axis, you should divide your variable x by such number, okay? Now, if you what you want to do is stretch by a factor of 1/2, in other words, like a compression, so to speak, now you have to multiply the variable by 2. I know this is more complex than before, but try to get used to such concepts, okay? So this is how stretches in the horizontal sense work. And like I repeat, these are more complicated than the vertical stretches. Let's see how it looks in this case. If I want to stretch this circle in the horizontal axis, only in the horizontal axis, by a factor of 2, say, what I have to do is multiply my variable, or in this case, divide, I'm sorry, by 2. Like so. There it is, okay? If you notice, this is the original function. This is your horizontal stretch by a factor of 2. Okay, so you are elongating the circle. And what I did was dividing the variable over 2. You see? Now, if you want to do the opposite, if you want to do your stretch so that it looks like a compression by a factor of 2, like if you want to make the circle slimmer or thin, then what you have to do is have your same function, which is the square root of 16 minus x squared, but multiply only the variable by 2, like so. You see what's happening? Okay, So just memorize these peculiarities about the horizontal stretches. Vertical stretches are I think are more intuitive, or more, they make more sense more or less, and the only difficulties to understand are these ones. Okay, and you're gonna take some time, or yeah, you're gonna have to have some time in order to get used to these concepts. Okay, guys, so that's how stretches both vertically and horizontally work. Now we can put all of these transformations together in order to create like more complex behavior. For example, look at this parabola. This is my parent parabola. Very nice and all. And what if I tell you that I want to create a function g, such that it's going to be such that its graph is going to be this one, but reflective about the x-axis and also displaced 2 units below. So what I mean is this, and I'm gonna first try to draw it in order for you to see what I mean. So I want to have the same parabola but reflective about the x-axis and then move downwards 2 units. So what I want to see is this. Like that would be the first thing I want to do. I want to reflect it about the x-axis and then move it or translate it 2 units downwards. So this is my final result. I want this, the blue one. I want this. This is this one, but reflected about the x-axis and then moved downwards or translated downwards 2 units. How can I achieve that? By creating a function g. Let's see. First, I work in reverse order from stretches and then reflections and then translations. That is the way in which you have to work. I repeat that. First, you're gonna perform stretches and then reflections, and at the very end the translations. So first, reflections. I want to reflect this one, so I write minus x squared. You see, that's my reflection. And then I'm gonna move it 2 units downwards. There it is. You see? So this new function g is actually applying two types of transformations to my original function f. Okay, which in this case are a reflection about the x-axis and then a translation of 2 units downwards. Why do I say to take order into account? Because if I wanted to do the opposite, if I wanted to first, let me get rid of this. If I wanted first to perform the translation first and then the reflection, what's going to happen is this. Look, again, what is my original function? X squared. So I'm going to write x squared. And then I'm going to translate it downwards by 2 units. There it is. Okay. And then I'm going to perform the reflection, which is achieved by multiplying all by minus one, right? Which is going to look like this. There it is. And you can see that it's not what it is not what we wanted. You see? So G and H are not the same. What we wanted was that. Okay? Now, if you wanted to achieve this, that's perfectly okay, right? I mean, there's nothing wrong. But you have to take into account that the order does matter. It's not the same as performing stretches and then translations, or the opposite. Let's do another example. Okay, what if I want to do this? Again, one more time. This is my parent function, x squared. Now, what I want to do is, let's say that I want to stretch it by a factor of 2 in the horizontal axis. Okay, I want to stretch it on the horizontal axis by a factor of 2. So I want to make it a little fatter, like so. It's gonna look like that, more or less like so. That's the first thing I want to do. Okay, horizontal stretch by a factor of 2, and then I want to displace it or translate it horizontally 3 units to the left, so that it's gonna look now like this, more or less. Let me get rid of the previous one, and then I want to translate it 2 units upwards, so that my very final thing will be, I hope I have not confused you with all of that. Did I say 2? Okay, let's say 2. This is gonna be my final thing. Okay, so first I want to make it fatter by a factor of 2 in the horizontal axis. Then I want to move it horizontally by 3 units to the left, and then I'm gonna translate it vertically 2 units upwards. So let's see how that will work. Remember, first stretches, then reflections, and then translations. So the first stretch is by a factor of 2 in the horizontal axis. So that should look like this. Okay, remember, when you want to stretch by a factor of 2, you divide the x over 2. When you want to stretch horizontally by a factor of 3 and make it even fatter, you have to divide the x over 3. Okay, so that is the first thing I wanted to do. Now, what was the next thing? Move it or translate it to the left by 3 units. So when we translate my function, my function, which in this case is this one, okay, to the left, I need to add to the variable as many units, which in this case will be 3. There it is. You see? To the variable only. And now, finally, if I want to translate it vertically 2 units, I add to the whole thing, to the whole function now, I'm going to add 2 units. And there you go. You see? Now, I understand that this can get very complex, and you have to have some practice. I mean, don't worry, guys. You can always experiment with this software or your TI, and so just experiment. Just experiment. If you think that it's some way and you perform it and it's not the way it is, well, you have to go back to the drawing board and do it again, right? And that's it. Okay, so don't worry, because these types of transformations, of combinations of transformations, can get quite tricky. So do it very slowly, think about what you're going to do, and proceed in the stipulated order. First stretches, then reflections, and at the very end translations. So that's it, guys. Now I'm going to just leave you with something very cool, a YouTube video that I saw a lot of years ago, in which how these things are applied in industry, in this case in Pixar. I mean, I don't know if you like those movies. I do like them, most of them. I was raised with Toy Story and all these things. And let's see what the main scientist from that company, Pixar, tells you about these ideas.
At Pixar, we're all about telling stories. But one story that hasn't been told very much is the huge degree to which math is used in the production of our films. The math that you're learning in middle school and high school is used all the time at Pixar. So let's start with a very simple example. Anybody recognize this guy? Yeah. So this is Woody from Toy Story. And let's ask Woody to, say, walk across the stage from, say, left to right, just like that. So believe it or not, you just saw a ton of mathematics. Where is it? Well, to explain that, it's important to understand that artists and designers think in terms of shape and images, but computers think in terms of numbers and equations. So to bridge those two worlds, we use a mathematical concept called coordinate geometry, right? That is, we lay down a coordinate system, with x describing how far something is to the right and y describing how high something is. So with these coordinates, we can describe where Woody is at any instant in time. For instance, if we know the coordinates of the lower left corner of that image, then we know where the rest of the image is. And in that little sliding animation we saw a second ago, that motion we call translation, the x-coordinate started with a value of 1, and it ended with a value of about 5. So if we want to write that in mathematics, we see that, that the x at the end is 4 bigger than x at the start. So in other words, the mathematics of translation is addition. All right? How about scaling? That is, making something bigger or smaller. Any guesses as to what the mathematics of scaling might be? Dilation? Multiplication, exactly. If you're going to make something twice as big, you need to multiply the x and the y coordinates all by 2. So this shows us that the mathematics of scaling is multiplication. Okay? How about this one? How about rotation? Right? Spinning around. The mathematics of rotation is trigonometry. So here's an equation that expresses that. It looks a little scary at first. You'll probably get this in 8th or 9th grade. If you find yourself sitting in trigonometry class wondering when you're ever going to need this stuff, just remember that anytime you see anything rotate in one of our films, there's trigonometry at work underneath. I first fell in love with mathematics in 7th grade. Any 7th graders? A few of you? Yeah. My 7th grade science teacher showed me how to use trigonometry to compute how high the rockets that I was building was going. I just thought that was amazing, and I've been enamored with math ever since.